mu. So since it's so simple, let me actually do the calculation. Put it up to the side here. So minus s, just to not worry about the minus side, is the expectation of log of p of n. But log of, we have we have p of n, so what is log of p of n? It's log of 1 minus mu plus n log mu, right? We want to take the expectation value of that. Log, but this is just a number. So its expectation value is itself. And this is a number, log of mu, it comes out. So it's just simply expressed in terms of the expected, what do you call it? Expected number of bosons, in that way of talking. Expectation value of n. And then, well, we could easily compute that too, but this is a very well-known formula. And if it's not, it's worth committing it to memory, which is that, now we just recall, this for bosons, that the expectation value, at temperature T, this formula, which is written in terms of mu, it's by definition of mu. There it is, e to the minus. So e to the beta omega is 1 over mu minus 1, which is equal to just mu over 1 minus mu. Right? So if we plug in that, mu over 1 minus mu, for that expectation value of n, then obviously you get this formula.
Can I ask a question?
That's the proof of it. Yes.
This calculation, you never mentioned what algebra this is a state on. Now did you mention that this has a unique decomposition in terms of extremes?
Right, so that would be a broader framework. So I think I said in the beginning, I said I'm going to be absolutely orthodox and traditional and just work with the Hilbert space and a density matrix in the Hilbert space.
But unless you give me the observables, I don't know whether this is, how do I compute entropy?
Well, we are computing it. So
I know it's a formula, but what does it mean? What I mean is, the state has to be applied to an algebra and shown that there's
no, but you're using a more sophisticated notion of state. I'm just using state equals density matrix.
I don't know.
What is the question? So, it's a simple harmonic oscillator algebra, right? What is the...
I know, but it's normal, the definition I know is, this is a formula, okay? But if you give me a state, it is a state on an algebra, okay? Then you're supposed to show, when you apply this kind of formula, that what is this, there's a unique extreme decomposition or whatever.
No, wait a minute. If you look in a textbook of quantum mechanics, they don't
but they
talk
also
about
treat
C-star algebra, at least most textbooks don't.
I know, but they also treat wave
C-star
functions.
algebras, and they don't what?
They also treat wave functions as functions.
Yeah.
So, okay.
Well, right, so one could be much more mathematically correct and one could be more general physically, and I think it's worth doing that. So I could tell you, as a separate thing, I could try and sketch how this fits into that more general framework. And in fact, I think to the extent that there's a difference between these two formulas that I've mentioned here, this one and this one, it might be that this one is a little more general and allows for situation. Let me not say too much. Let me not try to say exactly the difference in that case. But let me say that the framework that you're objecting to will not handle a situation in which the algebra does not admit an irreducible representation.
Yes.
And so if you're interested in algebras that do not admit for the algebra together with a state such that you cannot irreducibly represent the algebra and the state as a density matrix in that Hilbert space, then you have to be more general. But I'm not in that situation here. So I could try and if we had more time, I could take a few minutes out now and try and justify the formula, which everyone knows and which you find in every textbook. I could try and justify that as entropy defined as a sum of some expression like p log p, which represent the coefficients of extremal states in the convex set of all states on that algebra and so on. But I'm not going to do that. Maybe it's worth saying that that is a more general viewpoint, and one can prove that in this situation it yields exactly the standard everyday formula of trace row log row.
I am not objecting to the formula in this case, but in fact, this particular algebra, this is a KMST.
Yes.
So it has this modular, what is it? This KMS condition is fulfilled, and the commutant is in fact commutative algebra on which it acts, where you are applying this formula is exactly equal to that. It's a huge degeneracy.
But you're not disputing this formula, right?
No, but that proof, or at least I have seen, is highly non-trivial, despite the existence of a degeneracy.
No, well, we can talk later. I think that one can prove, as long as you have an irreducible representation, I think you can prove it in full generality that this trace of row on row.
But this is not irreducible.
No, it is.
No, the commutant is exactly
Well,
the same.
I'm not sure. The q's and in terms of the q's and the p's, it's an irreducible representation. It's just the usual Heisenberg computation relations. But I'm not sure I see the problem. But anyway, I think as long as we agree that this formula is valid, even if it could have a more general underpinning, then we can agree on the answer being valid too. So this is the expression we'll need, and then now we can just carry on with this plan, considering, well, the idea now is to produce a density matrix for one degree of freedom that has this form, but where we know the value of the entropy. So it's a bit of a trick. In principle you could say, let me diagonalize this Gaussian density matrix somehow. I don't know actually how to do that directly, but I'm sure it can be done somehow. But by using a little bit of a trick, we can bypass that and find the value of the entropy without ever explicitly directly diagonalizing the density matrix row. So let's do that. So the next subtopic is two coupled harmonic oscillators. And I believe it's called a squeeze state, but I'm not sure I've got the terminology right. If not, someone can correct me. So let's just recall something. For a single oscillator, just remember that, roughly speaking, the ground state psi of x looks like, or the ground state is just some sort of Gaussian like that. We'll see, well, I don't know actually why I'm recalling that, but anyway, it's true. So now let's consider, for the pair of harmonic oscillators, I'm going to introduce a positive number parameter gamma and consider, well, so first of all, the ground state for that pair would just be, of course, these are not interacting harmonic oscillators. So the ground state for them is just a tensor product of the ground states for the one oscillator and the second oscillator. I'll just write it as 0, 0. Now, I don't want to put the 2 in the ground state, that would be useless because they're not coupled to each other. I just get the product of the 2 ground states. So what I really want to do is this state, which I believe is can be called the squeeze state, where A is the annihilation operator for the first oscillator, and B, so A and A star and B and B star are the creation and annihilation operators for the first oscillator and for the second oscillator. And this is equal to 1 minus gamma squared. If I expand out the exponential, then I get the sum from 0 to infinity of gamma to the n over n factorial times A dagger B dagger or star to the n times this 0, 0 state. But remember how the normalization works. So if I apply n copies of the creation operator, I get the nth excited state with the coefficient of square root of n factorial. It's the same thing here, so for the b, so I'll get 2 n factorial square roots in the numerator, and there's 1 in the denominator. And so it'll cancel out, and it'll just be simply 1 minus gamma squared times the sum from 0 to infinity of gamma to the n times the nth. Oh, I see, I kept the tensor product notation. Times the coupled, the entangled sort of state where it's the nth here and the nth here. Right? Okay. Now we want to trace out. We want to trace out the second oscillator and get this. So if this psi was the state of interest, then the associated density matrix, of course, is psi dagger, whatever you call this. And now we want to trace out the second oscillator from that. So what is that? That's equal to, when you write it out, you'll get the coefficient squared, so therefore 1 minus gamma squared. And then you'll get a sum of terms that look like n, m, where you're summing over independently n and n. But when you take the trace, of course, that'll force n equals m, because for each given oscillator, all the different energy levels are orthogonal to each other. So it'll just end up as a single sum, and it'll be the sum over n of gamma. Now gamma was squared here, so it's gamma to the 2n times n, right? You don't need this calculation anymore. Okay? Now this is a thermal state, right? So it's just, again, a linear, incoherent superposition of the different energy levels with a harmonic progression, whatever that's called, coefficient. In fact, it's just of this exact form here if we identify mu equals gamma squared. So under that identification, this has the form of this density matrix, and therefore we know its entropy is exactly the same thing. So S of rho 1 is equals exactly to that expression minus log of 1 minus mu, or I can write it as gamma squared, 1 minus gamma squared minus gamma squared over 1 minus gamma squared log gamma squared. Just by either this formula itself or that formula with gamma squared substituted for mu gives the entropy of this. So we now have a density matrix whose entropy we know, but now we want to look at it in the position representation and see what it looks like, compare it with this form, and it'll have the same form, and then we'll be able to find the entropy of the density matrix of this form. So to do that, I have to make one. Oh, I was going to offer, since I think we have the strict cutoff, I won't do it. But if someone wants to ask later, it seemed to me that maybe I never actually, I mean, just because I'm trying to be complete, I don't think I ever actually proved that density matrix in full generality for the first system comes by tracing out the second system. I think that's sort of extremely well known to most people, but it may not be extremely well known to everyone. So I could have actually proved that in a couple of lines, but I'll skip it if someone wants to ask later. Okay, so now our aim is to find what this density matrix rho 1 whose entropy we know looks like in the Q representation for that first oscillator. And to that end, we notice the following thing. This is some sort of clever thing that defines this as a kind of Bogoliubov transformation of the ground state, of the ordinary ground state. That is, notice that if we apply A to this squeeze state, no one contradicted me, so I'll call it squeeze state. So if we apply A to this squeeze state, the annihilation operator of the first oscillator, then it's the same thing as applying B star times gamma to the second oscillator. So that another way of saying that is A minus gamma B star applied to this state equals 0, and B minus gamma A star, symmetry, applied to this state also equals 0. If we solve these, will be, I'll justify this in a second, and then after that, if we solve these equations as differential equations for psi q and q prime, we'll get the density matrix for this original state, and then we'll trace out, but using the Q representation, the second oscillator, and that'll give us the Gaussian state for the first oscillator, Gaussian density matrix for this first oscillator.
Why don't you just sandwich rho in Q and between Q and Q prime? That's what you want. You want the analog of that expression.
Yes.
So why not just sandwich it between?
Yeah, I could. I mean,
because the equality after the trace is just a wave.
I mean, maybe there's a better way of doing it. I wouldn't be surprised if there's a slightly simpler way, but if I were to do that, I think I'd get Hermite polynomials or some awful thing that I have to look up some identities and so on. This is some, snaking around, trying to do as little real work as possible, I suppose. Although we have to do a Gaussian integral. Gaussian integrals are work, but they're sort of mindless work. I mean, you just have to keep all of
You don't have to look at a book.
You don't have to think or look it up. You don't have to look at a book. You just have to be careful not to draw a sign or something like that. So, you certainly could do that. So, let me prove this. It's very simple once you're familiar with these kind of things. So A, just going back to the definition, and psi, it's kind of nice, but you haven't seen it. It seems clever the first time. So we want to apply e to the gamma A star B star 0. This is the full ground state, the 0, 0 ground state. But what we know is that A annihilates the ground state, right? So I can actually, I won't bother to write it again, we can actually convert this to a commutator because the second term vanishes. But this commutator we can work out. Now why is that? It's because A, this A regarded as a derivation of the algebra, now you're like, is equal to, this acts precisely as partial A star, right? Because when you commute A with A itself, you get 0. When you commute A with A star, you get 1. So it acts as if it was a derivative. So all I have to do is take the derivative of using that fact I have to take the derivative, I have to differentiate this expression with respect to A star. But what is that? That's just, so let's write it in quotes, partial A star of E to the gamma A star B star. All acting on ground state. This is of course just equal, if you just imagine expanding this out as a series, if you're not convinced by the playing around with the formula, this is just equal to gamma B star. Of course, everything here commutes with everything else, so there's no issue with factor ordering. And so it's just gamma B star times e to the gamma A star B star 0. Oops, I didn't have yellow. But anyway, that's equal to gamma B star times psi. Right? So that's the formula that we were aiming to prove. So we have these two. And now I'm going to I'm not going to go through every detail now, because it would take a little bit too long. So let me just say in words what we do. We now want to yeah, we don't need this. What we do actually. I think it's over there again. So now we want to know what is x, y. I think I'm going to slightly change the notation. Maybe I should. Yeah, okay, we want to know, psi of x, y for this ground state, which is equal to, which is in the direct notation equal to that. And we know this is the Schrödinger representation for the oscillator, so that we know P sub, let me call it, I called it Q. I think that was a mistake. I was calling the two momenta P and Q, but since I'll be using Q, I've used Q for something else, let me just call it P1 and Q2 is 1 over partial y, where, as usual, well, you can either, this is even more universally well known, but, or you can go back to what we found before, in the special case where W was just the identity matrix, and normalized properly, so we get the square root of 2 times A is equal to P minus IX, and the square root of 2 times D, the second annihilation operator, is Q, that changes then to P2 minus I times Y. Okay. And then you plug in this, so these two equations for the ground state, these define the ground state, of course. They just amount to, or to partial differential equations. This becomes, has some derivatives with respect to x, and this has some derivatives with respect to y and complex times. Anyway, these just become simple differential equations, and you can solve them by diagonalizing, making a change of variables. So if I define, I'll tell you the change of variables, and I won't go through it. If we define u as x plus gamma y, and v is equal to y, presumably xy plus gamma x, then the two partial differential equations decouple, so we get two, it looks now like two decoupled harmonic oscillators, and for those we know it's ground state. That was why I reminded you, now I know why I reminded you. You know it's ground state, you have to get the exact coefficient right here. Plug that in, so you get the ground state in terms of sort of e to the minus u squared plus v squared, just schematically, not exactly. And then transform back to x and y. This is a Gaussian, and you'll again get a Gaussian in terms of x and y. And so I'll tell you what the answer is. If you go through that little exercise, you get psi of x and y is equal to some normalization, which as usual which I call k, but usually we won't, as usual, we won't bother with it. So it's equal to 1 plus gamma squared, 1 minus gamma squared, x squared plus y squared over 2 minus 2 gamma over 1 minus gamma squared xy. That's what comes out just from the if you go through those steps. Okay, so that's the ground state for the two coupled harmonic oscillators. In this, not the ground state, it's the squeeze state for the two coupled harmonic oscillators. Gotten by, for those who are not familiar, I mentioned the word, but I should say again, this is basically what's called a Bogoliubov transformation. I don't know actually how it is in English, exactly. Some spelling like this. So you just mix, you have a set of two new annihilation operators that are made in linear combinations of the annihilation and creation operators of the original set. So, and that's what this is. It's really just a special case of a Bogoliubov transformation. So, that's just the name anyway.
But I'm guessing that the new creation annihilation operators, the commutator is like 1 minus gamma squared or something.
It's supposed to be, yeah, I might have not normalized them.
Yeah.
That's correct. These are probably not normalized correctly. But, so the correctly normalized annihilation operator will be some multiple of this object. And some multiple
this
of this object.
This squeezing is like an SL2R transformation. And that U and V relation that you have written there, if you put in that square root of 1 minus gamma squared, then you will see that it is an SL2R.
Yes, right. So another one is, okay, so now this gives us rho of xy. Again, it's just a pure state. So rho, the wave vector itself is a function of x and y, which are the configuration variables for the pair of oscillators. So the density matrix is a function of two of those, which we could call rho, which we could call x, y, x prime, and y prime, as usual. And since it's just a pure state, it's just given by the product. We've been through this all before. Only it's a little simpler now because it's only 1 degree of freedom. So psi of xy, psi of x prime y prime star, right? So that's the mixed state. Then rho 1, that's the density matrix for that squeeze state. And then the mixed state for the first oscillator alone. I guess I need a colon here if I'm doing it. What did here I use the colon, so here I'll use semicolon. So that's gotten by tracing out over the second oscillator, which in the position representation just means setting, well, we did this before, just means setting y prime equal to y and doing the y integral. So it's equal to the integral from minus infinity to infinity of rho of x, y, semicolon, x prime, but now y, not y prime, we set y equal to y prime times dy. Right? Which is equal to, well, we have it here, so we just need to do that integral. I'll just write it out again. It's equal to the integral of psi of x, y, psi star of x prime y dy. So that's what we need to evaluate, but that's a Gaussian integral. You can visualize, again, I won't bother doing this time. Last time we went carefully through, this time I won't bother doing the Gaussian integral explicitly, but just write this out. It's x prime and y prime, it's at x, set y equal y prime, do the y prime integral. You can see this is again a Gaussian density matrix, a Gaussian wave function. And you take the product as a Gaussian density matrix, and then the integral is just a Gaussian integral. So using that general formula. You can do it easily, and you get this result. Gaussian integration is conceptual.